Last time, we calculated the partition function for infinite range Ising model, and in the infinite spin limit or infinite site limit, this problem can be solved exactly by steep descent method that we discussed last time, that we could find the minimum point of y where this free energy is actually the minimum value, and then this partition function could be approximately given by that effective exponential function of free energy. Okay, and by minimizing the free energy with respect to y, and we can find the so-called self-consistent equation which determines the value of y or y bar at that minimum point of free energy. And we can also calculate the mechanization on any site of this model, and it turns out that this m is precisely the value of y bar, because this m is given by the derivative of the log with respect to the dimensionless field. And when we plug in this partition function at this minimum free energy point, y bar, and we simply get this simple relation. In other words, we need to solve this equation self-consistently, because on both sides of the equation, y bar involves. Okay, so then we should iteratively find the solution of this equation. But there's an easy way to get the solution, which is plot this two functions on both sides independently and look for the intersection. Okay, so suppose the y-axis refers to the any function which we call the g as a function of y, and g as a function of y could be either y or y bar, which is a yellow straight line here, or it could be a hyperbolic tangent function on the right hand side of the equation. So if the left hand side of the equation or the yellow line intersects with the dashed lines or the orange lines, orange curves, then we have a solution. If not, then we don't have a solution. Okay, so depending on the value of the beta j, whether this value is larger than or smaller than 1, and we could either have simply just one solution when beta j is smaller than 1, which is the high temperature regime, and is indicated by this orange curve here. In the higher temperature, there's only one solution, which is a 0, which means that there's no finite mechanization at high temperature. So this is reasonable, and this is also what we expect to happen at high temperatures. There's no spin order. And let's look at the low temperature limit when beta j is greater than 1, and we can find there are three intersections. One is 0, which is a trivial solution. Another right here and there, with a magnitude plus or minus m0, and we can see that there's two finite size solution plus or minus m0 will be our stable solution, and this trivial solution 0 is actually the unstable solution. So in other words, when temperature is low enough, then we could either find that the system has spontaneous mechanization with the magnitude m0 or minus m0, depending on which direction the field that we apply to. And the critical point happens when beta times j is equal to 1, which means that for a given coupling constant j, we could calculate the Tc, which is given by this relation here. So when T is at exactly Tc, then we have a phase transition. So we will come back to this sort of a mean field results later, but let's just look at the consequence of this solution. So we could expand this free energy Fm above this critical point, which is at that value, and we could try to Taylor expand this free energy near this critical temperature, and we find the following results. Okay, so you could Taylor expand this, say, the log or hyperbolic Koch function near this critical point, and this is the result. So we can expand up to, say, a fourth order, say in y bar, and then Forget about the higher order terms. And later we're going to analyze this free energy function near this critical point and get those critical exponents. So the way that we get the Taylor expansion is to Taylor expand this log Cauchy function when x is small, right? Okay, so let me just define this beta j is actually very close to 1, which is a critical value, but by a tiny amount of deviation, which I call this little t here. So this t is actually very, very, very small, close to 0, when we are very close to the critical point. So then we could rewrite this Taylor expanded free energy function near the critical point. So beta f now can be further expanded in terms of those polynomials of little t plus some constant terms like this. Okay, so we could simply consider the leading contributions in powers of t or y, and we could forget about the other terms. And this leading free energy near this critical point is our Landau's mean field theory. So which we will discuss later and come back this point again. Let's take a short break. When we come back, we will further try to minimize this f near this critical point with respect to y, and we get the critical exponent and so on and so forth. So we continue. So let me just provide you with more details when we perform this Taylor expansion of free energy close to the critical point. What I mean is that, remember, we want to solve this mean field equation or self-consistent equation to get the magnetization, and we know that in general there are 3 possible solutions or 3 possible intersections, but as we increase the temperature further and further, when we solve this equation by looking at the intersection points, and we see that as you increase the temperature further, or the value of beta j becomes slightly larger and larger, and you get the magnetization from the intersection where this intersection point, the value of this intersection point, which I call this m0 prime, for a larger temperature solution is much smaller than low temperature solution, or m0. In other words, the magnetization will decrease further and further if we further increase the temperature. So that's what we expect when we increase the temperature, that thermal fluctuations are going to suppress this magnetization. So at some point, we don't get any solutions anymore. So suppose the temperature is high enough, and we end up in the blue curve here, where beta j is actually larger than 1. So in that case, we don't get a solution. The solution is actually 0, which means that magnetization vanishes completely. So in other words, you get a continuous transition or crossover from the larger value of the magnetization, but as you increase temperature, the solution will get smaller and smaller value of the magnetization until the magnetization is fully suppressed beyond this critical temperature. But we are interested in describing the system close to this critical point or critical temperature or transition. In other words, we need to analyze the free energy close to that intersection point where this m0 prime is really, really small. In other words, this y or y bar close to transition is actually very, very, very small. And so is the field. Remember, for the one dimension, it's actually close to 0 temperature and 0 field. But in the infinite range Ising model, the transition occurs again close to 0 external field and very, very small magnetization remaining. So in that limit, we can expand around this free energy by expanding the hyperbolic cosine function. Remember, this h, both h and this y are very, very small. So for a fixed temperature or beta, the whole thing, which I call this x, is actually very, very small. So you could Taylor expand this Cauchy of x when x is small. That's what we get. And we could further simplify this by assuming that this y, or the magnetization, is very, very small. And we could simplify the free energy near the critical point to that form, which is the leading order in this parameter y and h and also t. Remember, little t is the dimensionless temperature close to critical temperature, whereas t is actually negative. Remember, we are coming from the low temperature ordered phase and trying to understand this transition from below. Okay, so near the critical point, all of the three parameters y, t, and h are very, very small. And in order to get the magnetization, we need to minimize the free energy with respect to y, the same that we get this magnetization by looking at the intersection. But now we are focusing on here. When everything is very, very small, we can Taylor expand the free energy, and still we are trying to find the y bar which minimizes the free energy. Okay, so this is what we do. So we minimize the critical free energy with respect to y, and we get the magnetization as a function of y and also h. So as I mentioned, at the critical point, this external field is actually 0. So when little h is 0, and we can find the solution of this little y. So y, there are three possible y values. One is 0, of course, it's trivial, but there's other two, plus minus square root of minus 3t. So coming from the solution of this equation by suppressing this little h. So note that this little t is actually negative, as I mentioned there. So therefore, the square root is actually positive. So this is a real number. So now you can immediately get the relation between this magnetization and this little t, which is the reduced temperature. So this m is actually proportional to t square root of t, t to the power of 1/2. So this is precisely the relation that we were looking for near the transition, meaning the magnetization vanishes in a power law fashion as the temperature approaches the critical temperature, and that power law exponent beta is found to be 1/2. So this is the first critical exponent that we calculate by this mean field theory. So this is a mean field prediction of this exponent associated with the magnetization, how magnetization vanishes as you approach this critical temperature. Okay, so we will come back to this next time when we study another mean field approach to the two-dimensional, three-dimensional Ising model. So this is just the first exponent that we obtained by analyzing the free energy close to the critical point. Second, so we could also study a relation between this magnetization and the field when we are sitting exactly at the transition temperature. So which means that when little t is exactly 0, or t is actually the same as tc. So in other words, we can plug in this relation back here. So when little t is actually 0, this little h is actually y power of 3. So it's a cubic relation to y or to magnetization. So which means that the field is actually proportional to m to the cube. And this is precisely the second important critical exponent which relates the magnetization and the field. So the field is actually proportional to magnetization to the power of delta, and here delta is 3. Okay, so this is the second critical exponent coming from this mean field analysis. Okay, so we can do more. The third quantity is actually the isothermal spin substitutability that we introduced earlier, which is the first derivative of this magnetization with respect to the external field, capital H, at a fixed temperature. So to get this first derivative of the m with respect to h, you could take the derivative of this mean field equation with respect to this h, and then by definition, the y, the h, capital H, is actually the same as partial m partial h, which is chi. And then you will find that this is proportional to h to the power of minus 2/3, which is from the previous relation that h is actually proportional to m cubed, and this is actually m to the power of minus 2. But we know that what is m in relation to this t, so this is a square root relation, and therefore this is proportional to inverse of t, okay, 1/t. And this is the third important relation which connects the isothermal substitutability close to critical temperature, which goes as a little t to the power of minus gamma, where gamma is actually 1. Okay, so by minimizing the free energy respect to this y, we get all the three critical exponents that we were looking for previously. So this is a very powerful and easy calculation that we can do. Okay, so let me summarize. This is beta 1/2, and gamma is actually 1, and delta is actually 3. So this is our mean field prediction for these critical exponents. Let us take a short break. When we come back, I will make a final remarks regarding the comparison between the mean field prediction and experimental data. Okay, so let's take a short break. So let me just make some final remarks regarding to the mean field predictions and how good they are regarding the predictions of the critical exponents, and short conclusions that the mean field predictions are reasonable agreement among mean field predictions and experimental data, and also the exact theoretical predictions for the Ising model in 3D. So in the middle, list the table that you can find in the textbook about all these critical exponents by various ways. So the first column is by the mean field theory, and the second is the experimental data for this fluid system. And the third column is the more exact results, theoretical predictions for this Ising model in 2D. And the last column is the more exact theoretical predictions of an Ising model in 3 dimensions. So you can see that the values of the first column agreed reasonably well. Of course, not that good, excellent agreement, but still they're not so far away from each other. You see the 3 red marked columns, all those numbers are in the reasonable agreement. It says 1/2 is not so far away from 0.3. Of course, there are systematic deviations between this mean field theory and all the other results. This is the final note. So you can see that throughout this mean field calculations, the dimensionality doesn't play any role, meaning all the critical exponents that we obtained do not depend on your spatial dimension, namely whether this is 1 dimension or 2-dimensional or 3-dimensional Ising model. It doesn't matter. So all the mean field predictions give you, for all these different dimensions, give you the same exponent over there, which is certainly wrong. So you can see that that's where this mean field theory fails, because we know that the critical exponents do depend on the spatial dimensions, as we'll discuss later. So this is one failure of the mean field prediction, where all the exponents do not depend on dimension, which they should depend on dimension. The second note is that the fluctuations beyond the mean field solutions are neglected here, which we'll address later. So this is some kind of a very crude approximation at the mean field level. And number 3 is that there are systematic deviations of the mean field predictions from either the exact results or the experimental data, as you can see from the table right here. To actually cure these deviations, we need to include the fluctuations beyond the mean field more seriously and rigorously, which will be addressed later. Okay, so this is the first and easiest, simplest way to get the critical exponent, which is the mean field theory. So let's stop here, and we will continue next week to actually formally introduce Landau's mean field theory for Ising model, which is slightly different but same in spirit to the calculation that for infinitely long-ranged Ising model that we just discussed right here. Okay, so I'll see you next time.